Hello everyone. Before I start my presentation, let me introduce myself briefly. I am Musharraf 4080. We are here today to present the paper titled Deep Learning Based Transcribing and Summarizing Clinical Conversations, a research study that explores how artificial intelligence can automate the documentation process in clinical environments. So, let's begin by outlining what we will cover today. So, here is a quick overview of our presentation. First, we will introduce the authors of the paper and the conference it was presented at. Next, we will explore the research motivation, why this topic matters, especially in clinical settings. Then we will break down the system architecture, showing the proposed solution works. And finally, we will cover the first core module, which is noise suppression. With that roadmap, let's start with the paper's background. So, the paper was authored by Niharika G. Menon, N.D. Bhavana, Avani Sravistava, and Judy Simon, all affiliated with the SRM Institute of Science and Technology, Chennai, India. It was presented at the fifth conference on ISMAC, which stands for IoT in Social, Mobile, Analytics, and Cloud. The presentation took place in November 2021. The paper has been published on IEEE Explore under the DO1. And as of now, it has 7 citations, which shows its impact in the field of medical aid. Let's move to the next slide. Next, let's now look at the problem. The paper addresses the motivation behind this research. Doctors today spend a significant amount of their time on administrative tasks like typing up clinical notes that, that not only takes time away from patients but can also affect the quality of care. The authors propose an automated system that can transcribe and summarize doctor-patient conversation using AI, specifically natural language processing and deep learning. Their goal is to reduce the manual workload by providing an efficient, reliable, and scalable solution to clinical documentation. This is especially important in scenarios like the COVID-19 pandemic, where the medical system are overwhelmed. So my teammate will start with the system architecture.
Good morning, everyone. I'm Aman Mafar, registration number 3807. My part is about the previous work that helped shape our project. Let's go through some research studies related to the topics we are addressing. The initial one is speech to text and classification. One research paper focused on converting speech to text and classifying medical sentences using models like logistic regression and SVMs. It achieved a high score but struggled with low sound, patient's voice, and limited data, especially for physical exams. This showed us the importance of creating strong and diverse medical data sets. The second one is speech enhancement. Another study explored the speech enhancement using RNN-based models for noise suppression and reverberations. This method works in simple environment but fail when dealing with a combined noise and echoes environments. This point out the need for advanced models like GAN, wavelet filtering, and CNNs models. The third one is clinical scribe challenges. One study examined the challenges of building a digital scribe from audio recording to extracting and summarizing data. It emphasized the need for higher quality audio and effective data extraction, which shaped how such systems should be designed. The fourth one is a digital scribing review. A review of a digital scribe system showed that the best performing one used context sensitive word embedding and attention based neural network. It also highlighted many commercial models are not publicly available, showing a gap between open and accessible research. The fifth one is voice and data fusions. One paper on clinical note summarization used a multi-hit attention model to find key phrases and applying token segment correlation and position embedding. However, it risks information and the sixth one is clinical concept extraction. A study on medical scribe datasets used a method called span attribute tagging (SAT) to label clinical concepts. There was a trade-off between recall and precision, making the model less flexible. The seventh one is clinical outcome representation. And the project used Biobird with ICD code hierarchies to predict clinical outcome from medical notes. It pointed out the need of more high quality dataset to reduce the impact of noisy labels. The eighth one is speech processing pipelines. The paper presented a basic pipeline involving speaker diarization and hierarchical RNNs and ontology-based taggings, but it lacked noise suppression and relied on more clinical usage, which limits its real-world impact. The ninth one is consultation summarization. A study about summarization found that only 20% of the conversation contains its relevant information for medical use. This supports the idea that systems should focus on extracting only the most important content. The last one is noise suppression. One paper introduced CGAN, a gen-based model for speech enhancement. It outperformed all the methods like Vena filtering and scoring methods, but it didn't fully remove all noise, especially high frequency sounds, leaving room for improvements. In summary, these studies showed a key challenges that still exist: a lack of high quality clinical data, difficulty in handling real world noises, and challenging in extracting structured and useful information from speech. This insight helps guide the direction and design of our project.
I'm Farhad ACM. Now we will dive into the core of our system, the three crucial modules that work into transform the clinical conversation into structured and usable data. These modules are noise suppression, speech-to-text transcription, and summarization and label. Each plays a vital role in ensuring the accuracy and utility of the final output. Let's move on to our first module, which is noise suppression. In real-world clinical settings, background noise is a significant challenge that can severely impact the accuracy of any transcription system. To tackle this, we implemented a sophisticated convolutional autoencoder model. This is not just a simple filter. This architecture is specially designed to learn and remove noise patterns while preserving the critical nuances of human speech. And also our model features 5 convolutional layers that process the input audio, extracting relevant features, followed by 7 deconvolutional layers that reconstruct the clean audio. A key component here is the conclusion of 6 skip connections. These connections are crucial because they allow important speech features from earlier layers to bypass deeper processing, preventing their loss during the noise reduction process. Think of it as a shortcut for essential information. Through extensive visual and subjective analysis, we observed a significant reduction in environmental noise. While there was a minor, almost negligible amount of speech loss in some instances, the overall improvement in audio clarity was substantial, setting a strong foundation for the subsequent stages. Moving on to the next slide. The transcription, we leverage the robust capabilities of the Google Speech-to-Text API. After the audio has been meticulously cleaned by our noise suppression module, this API takes over to convert the spoken words into written text. We choose Google's API due to its well-established and high accuracy to its ability to handle real-time streaming, which is essential for dynamic clinical conversations. Under the hood, the API utilizes an advanced LSTM or long short-term memory acoustic model This model is trained with connectionistic temporal classification or CTC, which is particularly effective for speech recognition tasks such as align speech with text without requiring pre-segmentation. And this technical choice allows for minimal memory usage and quick decoding, ensuring the efficiency. However, it is important to acknowledge some limitations. While highly accurate, the API still faces challenges with very heavy accents and highly specialized medical jargon. These instances often require custom training data to improve accuracy further, and this is an area where future enhancements can be explored. And finally, we have the summarization and labeling module, which is where the unstructured transcribed text is transformed into actionable organized data. The primary purpose of this module is to convert the raw text into a structured table, automatically extracting and labeling key information such as patient's name, their reported symptoms, prescribed medications, and their current medical conditions. To achieve this, we employed a combination of TF-IDF and bag of words speech extraction, which helps which helps the quantify the importance of words within the text. This extracted information then feeds into a support vector machine or SVM model. The SVM is crucial for classifying and organizing sentences into their respective categories within the summary table. Through the testing and hyperparameter tuning, using grid search, our summarization module achieved an impressive accuracy of over 94%. This high level of performance demonstrates its robustness and potential for real-world application in significantly reducing the administrative burden on healthcare professionals. That's it for my part. Thank you.
I am Ahmad MRR. When we see the results of the conference paper, we can divide the results into 3 parts. The first one is noise suppression module. They developed a convolutional auto encoder for denoising audio. They trained using clean and noisy audio samples. The results was they had a significant noise reduction and minor loss of speech clarity. So it need to be improved. So the next one is transcription module. They used Google speech to text API for transcription. They used both real-time and recorded audio for this. The benefits was domain specific adaptation and fast and scalable. The challenges was the accuracy drops with heavy accents and background chatter when using Google speech to text API. So the next one is labeling and summarization. They use TF-IDF in Ngrams for processing text and SVM for the classification parts. They categorized into patient details, symptoms, previous medications, and current situation as the categories of the summarized data. So the overall accuracy was 94.98 using SV. The final output was tabular summary for see the details of the patients for the doctors. So as a conclusion, they integrated solution using noise suppression, then transcription and medical summarization. So also created structured medical data from raw conversation, and they tried several models. They finally they found out the SVM was very accurate, so they used SVM. SVM was most effective among tested ones. So also there were some drawbacks, some speech distortion and classical machine learning limits in summarization. In the future scope, They mentioned explore advanced denoising methods using SEGAN and WaveNet, and the switch from SVM to deep learning to improve the model. Also, train on diverse real-world clinical data sets use the structured data for disease prediction, prognosis analysis, and scalable medical AI applications. Thank you.